A single point of light can outshine a trillion suns. That is the staggering reality of the brightest objects in creation, cosmic beacons powered by the darkest forces in space. We are about to unravel a profound paradox where the universe's ultimate voids, supermassive black holes, become engines of unimaginable light. By the end, you will understand how this violent partnership between light and dark actually built the galaxies we see today. We will explore how a destructive force can create brilliant structures and why the early universe was lit by monsters we rarely see now. What does this cosmic dance between creation and destruction reveal about our own place in the stars? That brilliant pinprick of light is called a quasar, the most luminous persistent object in the known universe. It is a beacon so powerful that a single one can outshine the combined light of every star in its home galaxy. Yet this is not a story of pure creation. It is a story of violent transformation, where light is born from the deepest darkness imaginable. This is the cosmic paradox at the heart of our journey. How can the ultimate symbol of darkness, a supermassive black hole, become the engine for the universe's most brilliant light? This idea feels almost mythological. Across countless cultures, creation stories often begin in a formless void, a darkness from which the first light emerges. The scientific reality we are uncovering echoes that ancient narrative in a breathtaking way. As astrophysicist Priyamvada Natarajan has eloquently framed it, we must stop seeing black holes solely as cosmic destroyers. In the grand scheme, they are also architects, shaping the destiny of galaxies with the very energy they unleash. So how does this alchemy work? The secret lies not in the black hole itself, but in the frenzied chaos just outside its point of no return, the event horizon. Imagine a whirlpool of cosmic material, a swirling, flat disk of gas and dust spiraling inward at nearly the speed of light. This is the accretion disk. As matter is pulled by the black hole's immense gravity, it does not go quietly. Particles collide, friction builds, and temperatures soar to millions of degrees. In this superheated maelstrom, gravitational potential energy, the energy stored by matter falling into a deep well, is converted directly into a torrent of radiation. It is the universe's most efficient power plant, but one with a terrifying core. The blinding light we see as a quasar is the final, radiant scream of matter being torn apart, its energy released only because there is an ultimate sink, a singularity, to create the gravitational gradient. This forces us to ask a profound question. If the brightest objects in creation are powered by the darkest forces in space, does this cosmic partnership force us to redefine our very ideas of creation and destruction? That frenzied light from the accretion disk is the signature of our first and most dramatic object, the quasar. To find them, we must look back in time to the early universe. This was a chaotic era, a cosmic soup of hydrogen gas and young, unsettled galaxies. In that primordial dark, quasars blazed like lighthouses, beacons of terrifying power that we can still see from billions of light years away. Their story begins with a mystery in the 1960s. Astronomers using radio telescopes found strange, star-like points that emitted powerful radio waves. They were called quasi-stellar radio sources, or quasars for short. But when Martin Schmidt examined the light spectrum from one named 3C273, he was stunned. The familiar pattern of spectral lines was shifted so far toward the red end of the spectrum that it could only mean one thing. This object was not a star in our galaxy. It was fleeing from us at an incredible speed, placed at a distance of over 2 billion light-years. For an object that looked like a faint star to be visible from that far away, it had to be emitting more light than an entire galaxy. Schmidt later described the moment of realization as a genuine shock, a complete overturning of expectations. The only conceivable engine for such staggering luminosity was a supermassive black hole, millions to billions of times the mass of our Sun, gorging on a vast feast of surrounding gas. We now understand the full anatomy of this cosmic powerhouse. At its heart sits the black hole, the ultimate sink. Around it spins that seething, luminous disk of doomed material, the accretion disk. And often, along the black hole's spin axis, magnetic fields can funnel some of the infalling matter into twin beams or jets that blast out at nearly the speed of light. These relativistic jets can extend for thousands of light years, sometimes appearing even brighter than the quasar core itself. Quasars were not just spectacular accidents, they were essential to galactic evolution. Their intense radiation and powerful jets acted like cosmic blowtorches, heating surrounding gas and regulating star formation. They essentially shaped their own homes. Their extreme brightness also made them perfect mile markers. By measuring their redshift, astronomers could map the expansion of the universe itself. But this leads to a curious observation. Quasars are far more common in the distant, early universe than they are nearby. Why? Because a quasar is a phase, a tumultuous teenage period in a galaxy's life. It requires a massive black hole and a tremendous supply of cold gas to fuel it. In the crowded, gas-rich early cosmos, galaxies merged frequently, funneling fresh fuel to the central monster. As the universe aged and galaxies settled, this fuel supply was either consumed or blown away by the quasar's own fury. The monster was starved, and the brilliant beacon faded into a quieter, but still massive, black hole at a galaxy's center. So what did the prevalence of quasars in the young universe tell us about galactic childhood? It revealed a violent, energetic adolescence where the brightest light was a direct symptom of the darkest force, a necessary chaos that ultimately brought order to the cosmos. The brilliant quasars of the ancient cosmos have quieted, but their legacy lives on in our galactic backyard. Point a powerful telescope at the heart of the nearby galaxy Messier 87, and you will find not a serene center, but a localized monster. A supermassive black hole, famously captured in an image, is still actively feeding, though not with the youthful voracity of a quasar. This is an active galactic nucleus, or AN, the broader family to which quasars belong. Think of AGN as the adult versions of those cosmic teenagers, still powerful but often more subdued and varied in their appearance. The key to understanding this whole menagerie of brilliant cores is a revolutionary idea called the unified model. It proposes a beautifully simple yet profound truth. The different types of AGN we see, from quasars to Seyfert galaxies to radio galaxies, are not fundamentally different beasts. They are essentially the same phenomenon, a supermassive black hole with an accretion disk and often jets, viewed from different cosmic angles and obscured by varying amounts of dust. This insight, pioneered by theorists like Donald Lyndon Bell, who helped unravel the physics of accretion disks, changed everything. It meant that our classification of these objects said more about our line of sight than about the engine itself. From one perspective, you might see a brilliant quasar. From another, looking through a thick donut of dust that hides the bright disk, you might only see the colossal radio jets shooting from the poles, labeling it a radio galaxy. And if that jet is pointed almost directly at Earth, you get the most violently variable object of all, a blazar. This brings us to the subtypes that populate our modern universe. Seyfert galaxies, like the beautiful Sombrero galaxy, have brilliantly shining nuclei but are otherwise normal spiral galaxies. Their central black holes are actively feeding, but on a more modest scale, allowing the rest of the galaxy's structure to remain visible. Radio galaxies, like Messier 87 itself, are famous for their enormous, often double-lobed jets that can stretch far beyond the visible galaxy. painting the intergalactic medium with radio waves. These jets are a testament to the raw power channeled by the black hole's magnetic fields. Then there are Blazars, where we stare directly down the barrel of a relativistic jet. From our vantage point, the jet's light is amplified and wildly unpredictable, flickering in brightness over days or even hours. This unified view forces a reflective question. Our own Milky Way hosts a supermassive black hole, Sagittarius a star, but it is currently quiet, with only a trickle of infalling gas. If it were to be fed a steady supply of fuel and become active, how would it appear from a distant world? Would we be a brilliant Seyfert, a radio-loud giant, or, if our jet aligned just right, a terrifying Blazar? This curiosity about perspective naturally leads us to the most extreme case, where the viewing angle does not just change the classification, it unleashes the most luminous transient events in the universe. A sudden spike of gamma rays, enough to outshine the entire galaxy it came from, all in the span of a coffee break. That is the terrifying reality of an object like Markarian 421, a Blazar whose brightness can fluctuate wildly in mere minutes. This is our third and most extreme object, where our cosmic perspective is not just a matter of classification, but of facing a direct, concentrated beam of raw energy. A Blazar is a specific type of active galactic nucleus, where one of those relativistic jets is aimed almost perfectly at our line of sight. We are not looking at the black hole from the side. We are staring directly down the barrel of the universe's most powerful particle cannon. The consequences of this alignment are dramatic, governed by a principle called relativistic beaming or Doppler boosting. As material in the jet races toward us at over 99% the speed of light, its light is compressed and amplified. It is the astrophysical equivalent of an ambulance siren rising in pitch as it approaches, but for light, making the jet appear hundreds or even thousands of times brighter than it would from the side. This also compresses the timescale of variations. A flicker that might take days to unfold within the jet appears to us as a violent flash lasting only hours or minutes. This is why Blazars dominate the high-energy sky. Astronomers working with instruments like the Fermi Gamma Ray Space Telescope note that these objects are among the most powerful and persistent sources of gamma rays we can detect. The entire electromagnetic output of the Blazar, from radio waves to the most energetic gamma rays, is dominated by this single beamed jet pointed right at us. This makes them exceptional natural laboratories. The jets act as the universe's most powerful particle accelerators, far beyond anything we can build on Earth, slinging protons and electrons to energies that defy comprehension. They also serve as probes. As the light from a Blazar travels across billions of light years, it passes through the faint fog of starlight and magnetic fields that fills intergalactic space. By studying how the Blazar's light is affected, we can map this otherwise invisible cosmic medium. The prototype of this bizarre class is an object called Blandford-Znajek. Initially mistaken for a variable star within our own galaxy, it was later revealed to be a monster at a colossal distance. Its spectrum is famously featureless, lacking the telltale emission lines seen in quasars, because the blinding glare of the beamed jet drowns out all other light from the system. This forces a humbling thought experiment. Our privileged, aligned view gives us a front row seat to an incredible show, but it also skews our perception. For every Blazar we see, there must be thousands of similar active galactic nuclei with jets pointing harmlessly off into other parts of the cosmos. The sheer brilliance we witness is a trick of geometry, a cosmic lighthouse beam that happens to sweep across our planet. It reminds us that what we can easily see is often the exception, not the rule, in the universe. This beam of concentrated energy, however, does not simply vanish into the void. It travels outward until it slams into something, and the structures it creates are the final, lasting monuments to the black hole's furious power. that jet of energy does not travel forever. Eventually, it plows into the sparse gas that lingers between galaxies, a collision of unimaginable force. The impact creates vast, glowing structures called radio lobes, often visible only in radio waves. These lobes can be millions of light-years across, dwarfing the galaxy that birthed them. They are the final, lasting monuments to the black hole's fury, colossal bubbles of energy inflated over eons. This is the fourth and most expansive object in our story, the radio galaxy. It is a fossil record of past activity, a signature written across the cosmos. But to understand how such a colossal structure is born, we must venture into the chaotic engine room itself, the violent space surrounding the supermassive black hole. We often picture a black hole as a simple, dark void. The reality is far more dynamic. It is the heart of a frenetic, high-energy maelstrom where the laws of physics are stretched to their limit. This engine has distinct parts, each playing a crucial role in the transformation of matter into light. At the very center, according to our current understanding of gravity, lies the singularity. This is a point of infinite density where our known laws of physics break down. We cannot see it, and we may never fully comprehend it. It is the ultimate sink. Surrounding it is the event horizon, the point of no return. This is not a physical surface, but a mathematical boundary. Once anything, even light, crosses this threshold, it cannot escape the black hole's grip. The event horizon marks the edge of the visible universe from that point's perspective. Just outside the event horizon is a region called the ergosphere, where the black hole's immense spin drags the fabric of space-time itself along with it. Here, nothing can remain stationary. It is a cosmic whirlpool that imparts tremendous energy to any matter caught within it. But the true powerhouse, the source of all the brilliant light we observe, lies a bit further out. This is the accretion disk, a flat, swirling pancake of superheated gas and dust spiraling inward. As material orbits, it does not fall straight in. It follows a gradual death spiral, and this is where the magic happens. Friction between fast-moving layers of gas heats the disk to incredible temperatures, millions of degrees. This hot plasma glows fiercely, emitting torrents of X-rays and ultraviolet light. The energy source is gravitational. As matter loses orbital energy and spirals inward, that energy is converted into heat and radiation with astonishing efficiency. It is like water gaining speed as it rushes toward a drain, its motion transformed into turbulence and sound. The work of collaborations like the Event Horizon Telescope, which produced the first images of the shadow around the black holes in Messier 87, and our own Milky Way center, has given us tangible data about this environment. Their images show not the black hole itself, but the dark silhouette it creates against the glowing backdrop of its accretion disk. This reveals a critical boundary known as the innermost stable circular orbit. Inside this orbit, stable circular paths are impossible, and matter plunges rapidly toward the event horizon. The location of this orbit determines how much energy can be extracted from the infalling material before it vanishes. Not all black holes shine with the same fierce intensity, however. This depends on their feeding habits, specifically the style of their accretion flow. In a radiatively efficient accretion disk, often called a thin disk, matter is orderly and dense. Friction is high, converting gravitational energy into light with great proficiency. This is what powers brilliant quasars and luminous Seyfert galaxies. In contrast, a radiatively inefficient flow, sometimes called a thick disk or a chaotic advection-dominated flow, is more like a sparse hot cloud. The gas is so diffuse that particles rarely collide to produce radiation. Instead, the gravitational energy is swallowed by the black hole along with the gas, resulting in a dim, quiet core. A perfect example is the supermassive black hole at the heart of our Milky Way, Sagittarius, a star. It is a cosmic titan with over 4 million times the Sun's mass, yet it emits only a faint whisper of X-rays. It is currently starved, existing in a very low accretion state, with only a tenuous trickle of gas reaching its event horizon. This stark difference forces a pivotal question. Why do some of these cosmic monsters feast lavishly, lighting up the early universe, while others, like our own, endure a meager existence? The answer lies not within the black hole, but in the galactic environment that surrounds it. Gravity is the ultimate cosmic gatherer. While the black hole's event horizon is the final destination, the true feast begins far beyond its grasp, in the grand architecture of the galaxy itself. The darkest force in space works on a colossal scale to assemble the banquet that will ultimately become the brightest light. This gathering happens through several dramatic mechanisms, each a testament to gravity's patient, relentless power. The most spectacular is a galactic merger, when two galaxies slowly entwine in a gravitational dance lasting hundreds of millions of years. Their stars mostly pass by each other like ghosts, but their vast clouds of interstellar gas do not. These clouds collide, lose energy, and sink toward the newly merged galactic center. This creates a sudden, massive influx of fuel, a delivery of raw material directly to the doorstep of the supermassive black hole. It is like throwing gasoline on a smoldering ember, igniting a brilliant quasar phase that can last for tens of millions of years. But mergers are not the only way. Even in a solitary spiral galaxy like our own, internal instabilities can serve dinner. A rotating bar of stars at the galaxy's core can act as a cosmic funnel, gravitationally nudging gas inward from the spiral arms toward the central regions. This provides a steadier, more regulated fuel supply, perhaps powering a sustained Seyfert galaxy glow rather than a quasar's violent outburst. Then there are the individual catastrophic snacks. If a single star wanders too close to the black hole's tidal grasp, it can be stretched and torn apart in a tidal disruption event. This produces a short, brilliant flare of light as the star's material is briefly devoured, a single-course meal compared to the merger's endless buffet. Cosmological simulations reveal an even grander feeder system. Researchers who model the evolution of the universe see how the largest structures, the filaments of the cosmic web, channel vast rivers of primordial hydrogen gas into the nodes where galaxies form. Over billions of years, this steady inflow can continuously replenish a galaxy's central reservoir, setting the stage for recurring activity. With all this potential fuel, how bright can these monsters actually become? There is a theoretical ceiling called the Eddington limit. It represents a balance of forces, the point where the outward pressure of the radiation blasting from the accretion disk equals the inward pull of gravity. If an object exceeded this limit, the radiation would theoretically blow away the very gas that is feeding it, shutting off the engine. Yet, we observe objects that seem to shine far beyond this limit. How is this possible? The answer often lies in our perspective and the messy reality of accretion. In a blazar, relativistic beaming makes the jet appear artificially bright from our vantage point. In other cases, accretion might be chaotic and clumpy, not a smooth disk, allowing material to fall in dense bundles that briefly radiate with extraordinary intensity before the radiation can push everything away. We see echoes of past feasts across the cosmos. A remarkable example is Hanny's voorwerp, Dutch for Hanny's object. This is a massive, ghostly green cloud of gas floating near a galaxy. The cloud is not producing its own light. It is illuminated like a cosmic neon sign switched on long ago. The light source was a quasar in the neighboring galaxy that has since faded. The light from that past outburst took tens of thousands of years to cross the gap to the cloud, so we are now seeing a fossil glow, a memory of when that black hole was actively feasting. This leads to a profound question about the relationship between the monster and its home. Are these violent feeding frenzies merely destructive events, or are they an essential part of galactic growth? The emerging answer suggests a deep, symbiotic connection. The energy unleashed by the feeding black hole, its radiation and jets, acts as a cosmic regulator. It heats surrounding gas, preventing it from cooling and collapsing into new stars too quickly. In this way, the brightest objects powered by the darkest forces do not just shine. They sculpt, they control the pace of star formation and ultimately influence the final size and shape of their host galaxy. The feast, therefore, is not just for the black hole's benefit. It is a transformative event for the entire galactic ecosystem. The relationship between a galaxy and its central black hole is far more intimate than we ever imagined. We now observe a stunning cosmic correlation. Galaxies with very massive central black holes also possess bulges, their central swarms of stars whose properties are tightly linked to the monster's mass. This is not a coincidence. It is evidence of a profound dialogue, a cosmic feedback loop where the brightest object and its host galaxy grow together, regulating each other's destiny. This concept of feedback is the master key to understanding galactic evolution. The energy unleashed by the feeding black hole, its radiation and jets, does not simply vanish into space. It slams back into the surrounding galaxy, controlling the very gas supply that fuels both new stars and the black hole's own feast. In essence, the darkest force in space learns to manage its own pantry, and in doing so, sculpts the light of billions of suns. Theorists like Blandford-Znajek, who run immense cosmological simulations, have shown how this works. When a black hole feeds vigorously in quasar mode, the intense radiation from its accretion disk creates powerful winds. These winds can blow away vast reservoirs of cold gas, the raw material for star formation. This process, called quenching, effectively puts the galaxy on a diet, slowing or even halting the birth of new stars. It is a dramatic example of radiative mode feedback, where the sheer pressure of light pushes against the infalling matter. But there is another, more subtle and persistent mode. In older, giant elliptical galaxies, the central black hole often feeds in a quieter, jet-dominated state. Here, the colossal relativistic jets, rather than blowing gas away, act like cosmic radiators. They drill into the hot gas halo surrounding the galaxy, inflating enormous bubbles and creating shock waves that pump energy into the environment, keeping it too hot to cool and collapse into stars. This is jet mode feedback, a long-term heating mechanism. We can see the evidence for this breathtaking interplay written across the sky. Look at the giant radio lobes extending from galaxies like Messier 87, fossilized bubbles of energy inflated by jets over millions of years. Even more striking are the observations from the Chandra X-ray Observatory of massive galaxy clusters, like the Perseus cluster. In the hot gas that fills the cluster, Chandra reveals vast, dark cavities, bubbles carved out by the jets from the central galaxy's black hole. Surrounding these cavities are subtle ripples, like sound waves from a colossal explosion, traveling through the intergalactic medium. These are the echoes of ancient Aegean outbursts, a direct record of the black hole's energy being deposited into its surroundings. This feedback loop solves a major puzzle. Why do the most massive elliptical galaxies in the universe today, filled with ancient red stars, show almost no new star formation? They possess plenty of gas, but it is kept hot and diffused by the occasional, precisely timed outburst from their central black hole. The monster, through its jets, prevents a runaway feast that would create too many stars, thus maintaining the galaxy's majestic, stable structure. This forces us to see black holes not as mere occupants but as governing hearts. Their violent brightness is a regulatory tool, a thermostat for galactic growth. The darkest force does not just create the brightest light, it uses that light to engineer the galaxy around it. The story of how we unraveled this cosmic partnership is a masterpiece of scientific detective work. It begins not in deep space, but in a field in New Jersey in the 1930s with an engineer named Carl Jansky. Tasked with finding the source of static interfering with transatlantic radio calls, he built a strange, rotating antenna. He traced the noise to 3 sources: thunderstorms, distant storms, and a persistent hiss that rose and set with the stars. That faint hiss was the first detection of radio waves from the Milky Way's core, the birth of radio astronomy. It opened a new window on the universe, one that would soon reveal invisible monsters. By the late 1950s, astronomers using new radio interferometers were mapping the sky, finding mysterious, compact sources of radio waves. The hunt was on to find their optical counterparts, the visible light from these radio beacons. The work of astronomers like Alan Sandage was crucial. Using the mighty 200-inch Hale telescope, he peered at the coordinates of a radio source called 3C48. Instead of a fuzzy galaxy, he saw what looked like a faint blue star. This was perplexing. Stars do not emit strong radio waves. More of these quasi-stellar objects were found, and their spectra, the chemical fingerprints in their light, were utterly bizarre. They made no sense until 1963, when Martin Schmidt had his breakthrough with 3C273. The strange lines were simply the familiar signature of hydrogen, but shifted incredibly far toward the red. The object was not a star. It was receding at nearly 16% the speed of light, placing it billions of light years away. For something that distant to appear so bright, it had to be unleashing the energy of 100 galaxies from a region perhaps no larger than our solar system. This revelation sparked what historians of science call a paradigm shift. The universe, it seemed, contained engines of a scale and power previously unimaginable. But what could possibly be that small and that luminous? The rapid flickering in brightness of some quasars over days or even hours provided a vital clue. Since light takes time to travel across an object cannot vary in brightness faster than light can cross it. These quick changes meant the powerhouse was tiny, perhaps just light hours or days across, smaller than the orbit of Pluto. Only one known physical object could pack so much mass into such a tiny volume, a supermassive black hole. Yet a black hole alone does not shine. The final piece of the puzzle was the accretion disk model, developed by theorists like Donald Lynden Bell. It described how gravity could power the brilliance, transforming the energy of infalling matter into radiation. Later, the work of Roger Blandford and Blandford-Znajek provided the elegant mechanism for the jets. They showed how the spinning black hole's immense rotational energy, coupled with powerful magnetic fields threading the accretion disk, could be tapped to launch and collimate those relativistic beams. This entire journey was enabled by technology, from Jansky's rotating antenna to space telescopes that could see the X-rays emitted by the searing hot disk, radiation blocked by our atmosphere. It was punctuated by fierce debates, like the one over whether quasars were truly at cosmological distances or some strange local phenomenon. Each argument was settled not by authority, but by the steady accumulation of evidence. This history invites a powerful reflection. Every tool we built revealed a universe more violent and wonderful than we had dreamed. So what current mystery, perhaps the nature of dark matter or the origin of fast radio bursts, awaits its own Carl Jansky or Martin Schmidt, waiting for a new tool or a flash of insight to reveal an even deeper layer of cosmic truth? Gravity provides the pull, but something else must shape the scream. Within that chaotic whirlpool of superheated plasma, an invisible architecture is at work, twisting the raw power of the fall into focused beams of light. This is the role of magnetic fields, the dark force's own invisible hand. Imagine the accretion disk not just as a hot gas, but as a sea of electrically charged particles, a plasma. Within this seething material, magnetic field lines are frozen in place, dragged along by the disk's furious rotation. As the inner parts of the disk spin faster than the outer parts, these field lines get stretched and wound up like trillions of rubber bands being twisted tighter and tighter. This creates immense tension, a stored energy that must eventually snap. This magnetic tension is not just a side effect, it is the essential mechanism that solves a critical puzzle. Gravity alone can make matter fall and heat up, but it cannot explain the breathtakingly organized collimated jets that shoot out from the poles. For that, you need a dynamo, a way to generate and harness electromagnetic forces on a cosmic scale. The key to turning the disk into an efficient engine is likely a phenomenon known as the Magnetorotational Instability, or MRI. As plasma astrophysicist Dmitry Uzdensky describes, this instability acts like a cosmic mixer. In a differentially rotating disk where inner orbits are faster than outer ones, weak magnetic fields create a kind of magnetic friction. This friction transfers angular momentum outward, allowing material to spiral inward while also generating the turbulence that makes the disk so brilliantly luminous. It is the MRI that likely turns a smooth flow into the effective, radiant maelstrom we observe. But the true marvel of magnetic engineering happens even closer to the abyss. Two landmark theoretical processes describe how the black hole's energy is ultimately extracted. The first, the Blandford-Payne process, focuses on the accretion disk itself. Here, magnetic field lines anchored in the disk act like tethers. As the disk rotates, it flings material outward along these field lines like a sling, launching and collimating the jets from the disk's surface. The second, even more profound mechanism is the Blandford-Znajek process. This taps into the black hole's spin itself, its rotational energy. The idea is that magnetic fields connect the spinning black hole's ergosphere to the external universe. As the black hole twists the fabric of space-time, it also twists these field lines, generating a powerful voltage that drives an electrical current. This circuit ultimately powers a jet directly from the black hole's rotational energy, like a cosmic battery with the singularity at its core. We are not just theorizing about these invisible structures, we are beginning to map them. The key tool is polarized light. When light scatters off electrons moving in strong magnetic fields, its waves become aligned or polarized. By studying the polarization patterns in the light from jets and accretion disks, astronomers can infer the geometry and strength of the magnetic fields shaping them. A stunning example comes from the Event Horizon Telescope collaborations follow-up observations of the jet from Messier 87. The polarized image reveals highly ordered magnetic fields wrapped around the jet, like the threads of a cosmic rope, providing the confinement needed to keep the beam focused across thousands of light years. This leads us to a pivotal question. If gravity is the dark force that gathers the fuel, are magnetic fields the universe's master translator? They take the chaotic, gravitational potential energy and convert it into structured, directed beams of light and matter. They are the unseen loom that weaves darkness into a brilliant, coherent pattern. This intricate magnetic architecture sets the stage for the final, most fleeting, and most energetic phenomena of all, where the full fury of this translation is unleashed in a single, catastrophic instant. Stretching over 1,000,000 light-years from its host, a filament of pure energy cuts through the darkness. This is the jet from Centaurus A, a structure so vast it dwarfs the galaxy that birthed it, a testament to the focused fury escaping a supermassive black hole. These are relativistic jets, the universe's most powerful particle accelerators, where plasma is focused into narrow beams and hurled across intergalactic space at over 99% the speed of light. They are not just byproducts, they are essential release valves. By carrying away tremendous angular momentum and rotational energy, they allow matter to continue spiraling into the black hole, powering the entire brilliant engine. To understand their fine structure, astronomers use a global network of radio telescopes linked together as a very long baseline interferometry array. This creates a virtual telescope the size of Earth, capable of resolving details in a jet down to scales smaller than a light year. What these observations reveal is astonishing: bright knots and shock waves within the jet that appear to move faster than light. This superluminal motion is a breathtaking illusion of relativity. If a jet is pointed nearly directly at us, material traveling almost at light speed is almost keeping pace with the light it emits. The successive waves of light arrive at our telescopes compressed in time, making the knot seem to cross vast distances in mere years, creating the illusion of impossible speed. The composition of these jets is a subject of ongoing detective work. They are likely a plasma, a soup of charged particles. The debate centers on whether the primary ingredients are lightweight electrons and their antimatter counterparts, positrons, or the heavier combination of electrons and protons. The answer changes how much power the jet actually carries. Keeping this torrent focused across millions of light years requires incredible collimation. This is achieved by the wound-up magnetic fields we discussed, which act like a constricting sleeve, and by the pressure of the surrounding gas, which squeezes the beam like a cosmic nozzle. When this beam finally slams into the tenuous gas of the intergalactic medium, it does not stop quietly. It plows into it, inflating colossal, radio-bright bubbles known as lobes. These are the radio galaxies we see, the lasting fossil records of the jet's power. The style of these structures helps classify the monsters that create them. In Fanaroff-Riley Type 1 radio galaxies, the jets are less powerful and appear to dissipate gradually, creating plumes or tails close to the host galaxy. In the more powerful Fanaroff-Riley Type 2 sources, like the famous Cygnus A, the jets remain tightly collimated until they violently terminate in bright hotspots at the outer edges of giant, symmetrical lobes, like twin explosions frozen in time. For a view of the most extreme end of this phenomenon, we look to the Quasar 3C279. As a blazar, its jet is aimed almost right at Earth, making it one of the brightest and most variable objects in the gamma-ray sky. From our perilous vantage point down the barrel, we see the full, Doppler-boosted fury of shocks and magnetic reconnection events within the jet, flickering with violent intensity. This forces a sobering reflection. What would the sky look like from a planet orbiting a star in the plane of such a jet? The gentle cosmic background would be drowned out by a permanent, searing beacon of high-energy radiation, a constant reminder of the violent heart at the galaxy's center. It is a perspective that underscores how these jets are not merely spectacular. They are transformative, carrying energy from the central darkness and depositing it into the furthest reaches of intergalactic space, shaping everything they touch. A star drifts from its familiar orbit, pulled by the subtle gravity of a sleeping giant. This is the prelude to a tidal disruption event, a stellar snack that briefly transforms a dormant supermassive black hole into a brilliant flare. It is our fourth object, a transient masterpiece of cosmic violence that reveals monsters we would otherwise never see. The star's fate is sealed by a simple battle of forces. As it approaches, the black hole's tidal pull on the near side of the star becomes overwhelmingly stronger than the pull on the far side. This difference, the tidal force, overwhelms the star's own self-gravity, the force that holds it together. The star loses that internal tug of war. It is stretched vertically and compressed horizontally, a process physicists call spaghettification. The star is pulled into a long, thin strand of glowing gas before it ever crosses the event horizon. This shredded debris does not vanish immediately. About half of it is flung away on hyperbolic orbits, lost to intergalactic space. The other half remains bound to the black hole, forming a chaotic, swirling stream of material. This debris then falls back onto the black hole over time, forming a temporary, incredibly hot accretion disk that shines with the light of billions of suns. This is the flare we detect, a beacon that can outshine its host galaxy for several months before fading as the last of the stellar material is consumed. The study of these events has been revolutionized by automated sky surveys. Astronomer Suvi Jazari, who leads teams using instruments like the Zwicky Transient Facility, explains that these surveys scan vast swaths of sky night after night, looking for anything that changes. A tidal disruption event announces itself with a sudden, bright point of light in a galaxy's center where none existed before. Its light curve, the graph of its brightness over time, has a characteristic shape, a sharp rise to peak luminosity followed by a gradual, steady decline as the debris is eaten. The flare emits across the electromagnetic spectrum, but its specific color tells a story. If we see a strong ultraviolet and optical glow, it suggests we are viewing the temporary accretion disk nearly face-on. A dominant X-ray signal might indicate we are looking through a hotter, more tenuous corona above the disk, or perhaps down the funnel of a jet. The variety is part of what makes them such rich laboratories. Most tidal disruption events are content to shine as brilliant thermal flares, but in a small subset, the infalling debris triggers the formation of a relativistic jet. This turns our already spectacular event into something far more extreme, a jetted tidal disruption event that can be seen across the universe in gamma rays and radio waves. A textbook example occurred in a nearby galaxy with the catalog name Assassin 14 Li. Discovered in 2014, it was close enough for telescopes to study in exquisite detail. Observations showed not just the flare, but also a wind of material blowing away from the black hole, and even the composition of the devoured star, which was rich in helium. It was a complete cosmic autopsy. This leads to the natural, if unsettling, question: could such an event ever pose a threat to life in its host galaxy? The reassuring answer is that the direct destructive effects are incredibly localized. The lethal zone of radiation is largely confined to the immediate galactic center, a region typically sparse with habitable planets. The real danger is not the flare itself, but the potential jet. If a jetted tidal disruption event occurred in our Milky Way and its beam were pointed directly at our solar system, the influx of high-energy radiation could severely damage planetary atmospheres. Yet the odds of a star wandering too close to our own dormant Sagittarius A star are astronomically low, and the further odds of that event producing a jet aimed precisely at us are more remote still. These stellar snacks, therefore, are less a threat and more a gift to astronomers. They are temporary flashes in the night that illuminate the quiet, supermassive black holes lurking in ordinary galaxies, revealing the dormant potential for violence that resides in so many cosmic hearts. This transient violence stands in stark contrast to the steady, enduring glow of our next object, a structure so vast it defies human scale. A brilliant, flickering pinpoint of X-rays in our own galaxy tells a familiar story. This is Cygnus X1, a stellar mass black hole locked in a tight orbit with a giant blue star. Every 5.6 days, it passes behind its companion, and for a few precious hours, we see only the star's light. This regular eclipse proves the X-ray source is incredibly small, a dark companion with a mass over 20 times that of our Sun. It is not a supermassive giant, but a stellar remnant, a black hole formed from a collapsed star. Yet, when we observe its behavior, the parallels are uncanny. It is a microquasar, a scaled-down, rapidly evolving version of the quasars that light the early universe. Here, in our own galactic backyard, we have a real-time laboratory where the violent physics of accretion and jet formation play out over days and weeks, not millions of years. The core components are all present, just in miniature. The compact object, be it a black hole or a neutron star, plays the role of the supermassive monster. The companion star, through stellar winds or by overflowing its Roche lobe, supplies a stream of gas. This gas spirals inward, forming a hot, luminous accretion disk. And often, from the poles of this system, relativistic jets of plasma are launched, stretching for light years into space. X-ray astronomers who monitor these systems witness something extraordinary: state changes. The microquasar can exist in distinct modes, governed by the rate of accretion from its donor star. In a low luminosity, hard state, the accretion disk is thought to be truncated, with a hot corona of electrons surrounding the black hole. This state is often associated with steady, powerful radio jets. As the accretion rate increases, the system may transition into a high luminosity, soft state. Here, the disk extends inward, glowing fiercely in softer X-rays, and the jets are typically quenched. It is a dramatic on-off switch for jet production that mirrors, in a fast-forward loop, the life cycle of its supermassive cousins. To see this physics in action, we can look at the microquasar GRS 1915+105, discovered in 1992. It is one of the brightest X-ray sources in the sky and a notorious show-off. Its light curve is not a steady line. It is a chaotic scribble of flares, dips, and oscillations. Astronomers have identified over a dozen distinct variability patterns, or heartbeats, each tied to the complex interplay between the accretion disk and the emerging jet. In one famous pattern, the system builds up a reservoir of hot gas in the inner disk, then expels it in a violent jet before the cycle begins anew. It is like watching a pressure cooker release steam over and over on a cosmic scale. Perhaps the most instructive microquasar of all is SS433, located about 18,000 light-years away. It is a system where a compact object, likely a black hole, accretes matter from a companion star. What makes it a landmark is its spectacular precessing jets. They are not fixed in space, they slowly wobble or precess, like a spinning top winding down, over a period of about 162 days. This precession is a clear sign of a warped accretion disk, likely caused by the misalignment of the disk with the black hole's spin axis. Studying this wobble gives us direct insight into the complex mechanics of how angular momentum and magnetic fields interact to shape and direct relativistic outflows. The existence of microquasars forces a powerful question. What universal principles are at work here? The answer is that the fundamental physics of magnetized plasma, gravity, and angular momentum are scalable. The equations describing how a disk heats up, how magnetic fields twist and launch jets, and how energy is extracted from a spinning object, they do not care if the central mass is 10 solar masses or 10 billion. The timescales are different, the energies are vastly different, but the underlying choreography is the same. A microquasar is a quasar played at 1,000 times speed, allowing us to observe a full cycle of activity within a human lifetime. This scalability is a gift, a confirmation that the violent processes we infer in the distant, ancient quasars are not just theoretical. They are happening right now in our own galaxy, in a form we can watch, measure, and finally begin to understand. The control room hums with a quiet intensity, screens glowing with data streams from across the cosmos. This is the modern hunt for the bright and the dark, where astronomers piece together the full story, not with a single telescope, but with a symphony of them, each tuned to a different slice of the electromagnetic spectrum. No single type of light can reveal the entire beast. To understand these cosmic engines, you must listen to every note they play, from the deep bass rumble of radio waves to the piercing shriek of gamma rays. Each wavelength band acts as a specialized probe, illuminating a specific physical process within the violent chaos. The Chandra X ray Observatory, for instance, peers at the searing hot inner regions. As an instrument scientist might explain, Chandra's sharp eyes capture X-rays emitted by the multimillion-degree plasma just outside the event horizon, mapping the superheated corona and the innermost accretion flow. It shows us where matter is undergoing its most violent transformation. The Hubble Space Telescope and its successors in the optical and ultraviolet see a different layer. They capture the glow from the outer, cooler parts of the accretion disk and the brilliant clouds of gas illuminated by the central engine's radiation. This light helps us measure the geometry and total energy output of the system. Then we shift to the radio sky, the domain of facilities like the Atacama Large Millimeter Array, or ALMA. ALMA exquisite sensitivity detects the long wavelength radiation from the colossal, magnetically confined jets and the vast, expanding lobes they create. It traces the architecture of the outflow, showing how energy is transported across galactic distances. At the highest energies, the Fermi Gamma Ray Space Telescope monitors the sky for the telltale flashes from Blazars and other extreme objects, capturing photons born in the most ferocious shocks within relativistic jets. This multi-wavelength approach is not just about taking pretty pictures in different colors. It is fundamental detective work. Timing analysis, for example, studies how brightness fluctuates across different bands. If a flicker in X-rays is followed milliseconds later by a flare in radio, it reveals a physical connection, perhaps a disturbance traveling from the inner disk out into the jet. Spectroscopy, the analysis of light's fingerprint, allows astronomers to measure the blistering orbital velocities of gas in the accretion disk, infer the black hole's mass, and even determine the chemical composition of material being devoured. A landmark example of this coordinated effort was the global campaign to observe our own galaxy's supermassive black hole, Sagittarius A*, during a rare and modest flare. Telescopes across the planet and in space, from radio dishes to X-ray observatories, trained their instruments on the galactic center simultaneously. The goal was to catch the same event in every possible light, to see how a small influx of material rippled through the entire environment, from the hot inner flow to the faint, wispy outflows. This data mosaic is still being pieced together, offering an unprecedented look at a monster's snack in real time. This evolving toolkit now extends beyond light. As gravitational wave astronomy matures with observatories like LIGO and Virgo, a profound question emerges. Could we ever detect the ripples in space-time from matter spiraling into a supermassive black hole? For stellar mass black holes, the signal is clear. For their supermassive cousins, the frequencies are too low for current ground-based detectors. But future space-based observatories, like the proposed Laser Interferometer Space Antenna, may one day tune into that deep, cosmic hum, listening for the gravitational waves produced by the final plunge of stars or even smaller black holes into these galactic giants. It would be the ultimate confirmation of the dark force's presence, a vibration felt through the fabric of reality itself, complementing the brilliant light we already see. The absolute darkness of an event horizon presents a perfect boundary, a one-way street from which nothing, not even light, can return. Yet Stephen Hawking proposed a revolutionary twist, a glimmer from the abyss itself. He suggested that black holes are not perfectly black. In a stunning theoretical marriage of gravity and quantum mechanics, Hawking showed that the darkest forces in space could have a hidden, creative output. This idea stems from a strange quantum rule. Even in a perfect vacuum, empty space is not truly empty. It seethes with fleeting fluctuations, where pairs of virtual particles, one matter and one antimatter, constantly pop into existence and then annihilate each other almost instantly. Normally, this dance leaves no trace, but near the event horizon of a black hole, the gravitational grip warps this delicate balance. Hawking theorized that if such a pair appears right at the edge, one particle could fall across the horizon while its partner escapes into space. To an outside observer, it looks as though the black hole has emitted a particle. This is Hawking radiation. The energy for creating this real particle comes from the black hole's own mass, meaning the black hole very slowly loses energy and shrinks. In his landmark book, A Brief History of Time, Hawking presented this with elegant simplicity, transforming a mathematical prediction into a profound cosmic concept. For the supermassive black holes we have been discussing, this radiation is unimaginably faint, a whisper completely drowned out by the roaring brilliance of an accretion disk. The temperature of the Hawking radiation is inversely related to the black hole's mass. A stellar mass black hole would be slightly warmer than the cosmic microwave background, while a supermassive one would be far colder than the space around it, making its theoretical glow utterly undetectable with current technology. This leads to a deep and unresolved puzzle, the information paradox. Quantum mechanics states that information about what falls into a system can never be truly destroyed. But if a black hole evaporates completely via Hawking radiation, and that radiation is purely random and thermal, what happens to all the information about the stars, gas, and planets it consumed? Does it vanish, violating a core quantum principle, or is it somehow encoded in the radiation or preserved on the horizon? This remains one of the greatest theoretical battles in modern physics. We can contemplate a distant future, trillions upon trillions of years from now, when the universe has expanded and cooled. In that silent, dark era, a lone, primordial black hole, with no accretion disk to feed it, would finally begin to shine in its own right. As it evaporates, its temperature would rise and its glow would intensify. The final moments might be a sudden, bright pop of particles as the last of its mass converts to energy. This theoretical end stands in stark contrast to the violent, brilliant emissions of an active galactic nucleus. It suggests that even the ultimate cosmic sinks are not eternal, that they possess a faint, intrinsic glow born from the quantum vacuum itself. So while we cannot see it, Hawking radiation offers a profound philosophical insight that in the universe's deepest darkness, there may always be a mechanism, however slow and subtle, for something to emerge. The cosmic web is a scaffold of invisible threads, a hidden architecture upon which the luminous tapestry of galaxies is hung. While we have explored the direct partnership between black holes and brilliant light, there is another, more enigmatic dark force that may set the stage for this entire drama: dark matter. This mysterious substance, which does not emit, absorb, or reflect light, exerts its presence solely through gravity. Its indirect role is foundational, for it is the unseen hand that sculpts the universe's largest structures. Cosmologists who run simulations of cosmic evolution see a clear story. Vast halos of dark matter form first, creating deep gravitational wells. Ordinary matter, the gas that will become stars and galaxies, then flows into these wells. The size and merger history of a dark matter halo directly dictate the destiny of the galaxy that forms within it, including the growth of its central supermassive black hole. In this way, the darkest force we cannot see may be the ultimate architect for the brightest objects we can. This gravitational scaffolding does more than just provide a home. It may also influence the fuel supply. Some frontier theories propose more exotic interactions. One speculative idea suggests that in the incredibly dense environment right around a supermassive black hole, dark matter particles could be concentrated to such a degree that they annihilate upon collision. If dark matter is its own antimatter counterpart, these annihilations would release energy, potentially providing an additional, faint power source that supplements the traditional accretion disk. Another hypothesis considers the possibility of primordial black holes, tiny black holes formed in the universe's first moments, as a component of dark matter. If these exist, they could be captured by a supermassive black hole and slowly accreted, providing a long-term, steady trickle of mass. It is crucial to note that this is the cutting edge of theoretical astrophysics, not settled science. Researchers are actively looking for observational clues, such as correlations between the mass of a central black hole and the properties of its host dark matter halo. Does a more massive halo always lead to a more massive black hole? The answers could reveal a hidden dialogue between two forms of darkness. This expands our view of the cosmic players in a profound way. We began with a single paradox, a dark singularity powering brilliant light. Now we must consider a grander symphony where the invisible mass of dark matter shapes the stage, gathers the galactic fuel, and perhaps even whispers its own energy into the central engine. Could the darkest forces be a duo, the absolute darkness of the event horizon and the pervasive, elusive darkness of the cosmic web, working in an intricate billion-year concert to produce the beacons that illuminate the void? This possibility reminds us that our understanding of the cosmos is still unfolding, with each answer revealing a deeper layer of connection. The sheer pressure of light itself can become a cosmic barrier. An accretion disk shining with such ferocious intensity creates a torrent of photons, each carrying a tiny physical push. This radiation pressure is the universe's ultimate brake, setting a theoretical maximum on how bright any object powered by accretion can become. This ceiling is known as the Eddington luminosity, a fundamental balance point where the outward push of radiation exactly equals the inward pull of gravity. If an object tries to shine brighter, the radiation should theoretically blow away the very gas cloud that is feeding it, like a hurricane wind scattering leaves, starving the engine and dimming the light. The calculation for this limit is elegant in its simplicity, depending only on the mass of the central object. For a black hole with the mass of our Sun, the Eddington luminosity is about 1 trillion watts, a number so vast it feels abstract. Yet it provides a crucial yardstick. It also highlights the staggering efficiency of black hole accretion. While nuclear fusion in a star's core converts only about 0.7% of mass into energy, a well-ordered accretion disk around a black hole can achieve an efficiency of 10 to 40%. This is why a quasar powered by a supermassive black hole can outshine a galaxy full of fusion-powered stars, but nature, as always, finds loopholes. Astronomers observe objects that appear to be super-Eddington, shining with a brilliance that seems to defy this fundamental limit. Some tidal disruption events, for instance, show an initial peak luminosity that suggests a brief, catastrophic feast exceeding the Eddington rate. Even more perplexing are the ultra-luminous X-ray sources, or ULCs. These are point-like objects in other galaxies that are far brighter than any stellar mass black hole should be, yet not as bright as a full-blown supermassive quasar. For years, their existence was a major puzzle. How could they be so luminous without blowing themselves apart? The leading explanations involve clever geometry and different modes of accretion. One possibility is that we are seeing beamed emission, much like a blazar, where the radiation is focused into a narrow cone pointing at us, making it appear artificially bright. Another, more fascinating idea involves a radically different disk structure. Instead of a thin, orderly disk, matter may pile up in a thick, dense torus often called a slim disk. In this configuration, radiation struggles to escape outward. It becomes trapped within the flowing gas, advected inward with the material like smoke caught in a swift current, allowing more matter to fall in before the radiation can push it all away. A nearby laboratory for this extreme physics is the starburst galaxy Messier 82, a turbulent place of rapid star formation. Nestled within it is an ultra-luminous X-ray source that fluctuates wildly. Some astronomers propose it is a stellar mass black hole or a neutron star feeding at a super-Eddington rate, perhaps through a slim disk or via a dense, focused wind from a massive companion star. Within such a chaotic flow, instabilities like photon bubbles might form. Picture a pot of thick soup coming to a boil, where bubbles of radiant energy buoyantly rise through the denser fluid, creating channels that allow radiation to leak out more efficiently than a uniform wind, potentially enabling a sustained supercritical flow. Observing these objects is like watching the universe's most powerful engines redline, testing the very limits of our physical models. It forces us to ask, are we witnessing known physics operating in its most extreme regime, or are we seeing hints of something entirely new, a realm where the standard rules of balance are rewritten by sheer, overwhelming flux? The universe's history is written in the fading of its brightest beacons. We live in a cosmic Middle Age, a relatively quiet era compared to the brilliant fireworks of its youth. If we could rewind time to when the universe was only about 2 to 3 billion years old, the night sky would look profoundly different. This period, often called cosmic noon, was the golden age of quasars. The cosmos was ablaze with these brilliant monsters, far more numerous and active than they are today. This grand narrative of cosmic evolution, from a fiery adolescence to a more sedate maturity, is not just a story about black holes. It is the story of how the universe itself grew up and how the brightest objects were the architects of that change. The evidence for this dramatic shift comes from monumental surveys of the sky. Projects like the Sloan Digital Sky Survey have painstakingly mapped the positions and distances of millions of quasars, creating a three-dimensional census of the universe's most luminous objects. When astronomers plot the number of quasars against cosmic time, a clear pattern emerges. The curve rises steeply, peaks sharply around cosmic noon, and then declines just as steeply into the present day. The early universe was a vibrant, crowded, and chaotic nursery. Galaxies were smaller, gas was abundant and cold, and colossal mergers happened with startling frequency. Every major collision funneled vast reservoirs of fresh fuel toward the central supermassive black hole, igniting a brilliant quasar phase that could last for tens of millions of years. The universe was lit by the violent birth cries of galaxies, but nothing that bright can burn forever. The explanation for the fading of the beacons is a story of resource depletion and self-regulation. As the universe expanded and aged, several key changes occurred. The rate of major galaxy mergers slowed. The pristine, cold gas that once filled intergalactic space was either consumed in star formation, heated by the radiation of those same stars and quasars, or blown into a diffuse, hot state by the powerful feedback from the black holes themselves. The monsters, in their brilliant fury, essentially burned through their available fuel and heated their surroundings so much that it became difficult for new, cold gas to reach them. They starved themselves into a quieter state. We see the end results of this process all around us in the local universe. Look at the giant elliptical galaxies that sit at the hearts of massive clusters. They are often called red and dead galaxies, not as a morbid description but a scientific one. They are dominated by old, red stars with little of the blue light from newborn stars or the violent glow of an active nucleus. Their supermassive black holes are present but dormant, like massive engines idling quietly with only a faint trickle of fuel. They are the cosmic retirees, living off the wealth of their earlier, more active years. The contrast is stunning when we compare new images from the James Webb Space Telescope of the early universe to our own galactic neighborhood. Webb reveals a tapestry of young, misshapen galaxies, often with bright, knotty cores actively building themselves. Our local universe, in comparison, appears more settled, structured, and calm. This evolutionary arc leads to a reflective question. Is the age of brilliant cosmic monsters largely over? For the universe as a whole, the peak of quasar activity has certainly passed. The readily available feast has been consumed, yet the potential for violence remains dormant, not extinct. In our own local group of galaxies, a future cosmic event is already written in the stars. The Milky Way and the Andromeda Galaxy are on a collision course, destined to merge in about 4 billion years. When that happens, the gravitational chaos will likely funnel fresh gas toward the central black holes of both galaxies. We could witness the reignition of a brilliant quasar, a final, spectacular flare of activity in our own celestial backyard before the merged galaxy settles into a quiet, elliptical future. The monsters may sleep, but they are never truly gone, waiting only for the next gravitational disturbance to stir them from their slumber. For a few fleeting seconds, it outshone the entire observable universe. In October 2022, satellites designed to monitor nuclear tests instead caught a flash of gamma rays so intense it temporarily blinded their instruments. This was JRB 221009A, later nicknamed the BOAT, the brightest of all time. A gamma-ray burst is the most powerful explosion known since the Big Bang itself, a concentrated beam of energy that can briefly outshine every star in its host galaxy combined. While not powered by the supermassive black holes we have been discussing, these cataclysms represent the same fundamental paradox on a different scale, where the birth of a new stellar mass black hole unleashes the most brilliant transient light in the cosmos. These events are classified by their duration. Long gamma-ray bursts lasting more than 2 seconds are linked to the collapse of a particularly massive, rapidly rotating star. As the star's core implodes, it can form a black hole or a highly magnetized neutron star called a magnetor. Around this new, compact object, a swirling torus of stellar debris forms. This hyper-accreting disk feeds the newborn monster at an incredible rate, powering ultra-relativistic jets that drill their way out through the collapsing star. The jet, moving at over 99.99% the speed of light, finally breaches the stellar surface, and its interaction with the surrounding material produces the initial, blinding pulse of gamma rays we detect. This model is called the Quasar scenario, and it directly ties the burst to a supernova, the explosive death of the star. Teams operating satellites like Swift and Fermi are trained for these moments. The instant a gamma-ray burst is detected, automated alerts are sent to telescopes around the world and in space, initiating a rapid follow-up campaign to catch the fading afterglow. Short gamma-ray bursts lasting less than 2 seconds have a different, equally violent origin. They are thought to be the signature of 2 neutron stars, or a neutron star and a black hole spiraling together and merging. In the final moments before collision, tidal forces rip the neutron stars apart, spraying a cloud of neutron-rich material into space. The merger itself likely forms a black hole, again surrounded by a fleeting, hyper-dense accretion disk. The jets launched in this scenario are narrower and even more energetic. The radioactive decay of the ejected material, rich in heavy elements like gold and platinum, produces a distinct glow called a kilonova, a cosmic forge for the universe's most precious metals. The initial gamma-ray flash is just the opening act. As the jet plows into the interstellar medium, it creates a long-lasting afterglow that radiates across the spectrum, from X-rays to radio waves. This afterglow is our key to understanding the event, allowing astronomers to pinpoint the host galaxy, measure the energy, and confirm the theoretical models. The case of the BOAT JRB 221009A was extraordinary. Even though it occurred nearly 2 billion light-years away, its photons were so abundant they ionized Earth's upper atmosphere and left a measurable echo in our planet's magnetic field. Follow-up observations revealed it was a long burst, firmly linking it to the death of a massive star and the likely birth of a stellar mass black hole. This forces a profound reflection. If quasars are the sustained roar of supermassive black holes feasting, our gamma ray bursts their opposite, the brief, piercing birth cry of a stellar-scale black hole. Both phenomena channel immense gravitational energy into focused beams of light through the same basic mechanism, accretion and jets, but operating on vastly different mass scales and timescales. One builds galaxies over eons, the other marks the violent end of stellar lives in an instant. Together, they bookend a universal principle, from the smallest to the largest scales. The darkest forces in space are inextricably linked to the most brilliant flashes in the cosmos. A new era of cosmic observation is about to begin, not with a single telescope, but with a synchronized orchestra of machines that will watch the sky in ways we have never before imagined. The future of understanding the bright and the dark lies in this coordinated assault, moving us from studying rare, brilliant specimens to witnessing the full, dynamic population of these monsters in action. It is the shift from still photographs to a continuous, real-time cinema of the cosmos. The first act in this revolution will be a relentless, automated scan of the entire visible sky. The Vera C. Rubin Observatory in Chile, with its enormous camera, will soon begin the legacy survey of space and time. Night after night for a decade, it will image the sky, creating a monumental movie of the universe. It will not just find new active galactic nuclei and tidal disruption events. It will discover millions of them, catching their flares from the very first glimmer. Scientists working on the survey note that this flood of data will let us see the full life cycle of these events, from ignition to fade, and understand how common they truly are across different types of galaxies. But to make sense of this deluge of data, we will need new kinds of assistance. Machine learning algorithms will be essential, trained to sift through the billions of detections and flag the subtle, rare signatures of a star being torn apart or a black hole waking from its slumber. This is population-level astronomy, where the story of cosmic evolution is written in the statistics of millions of flickering points of light. To understand the origins of these monsters, we must look back to the very dawn of time, and for that we need the James Webb Space Telescope. Webb's infrared eyes are peerless for piercing the cosmic dust and redshift that shrouds the universe's first billion years. It is already finding surprisingly massive black holes powering quasars in that infant cosmos. The pressing question Webb seeks to answer is a chicken and egg puzzle of galactic proportions. Did the first supermassive black holes form from the direct collapse of immense primordial gas clouds, seeding galaxies around them? Or did they grow from smaller, stellar mass black holes that merged and fed rapidly in the dense early universe? Webb's detailed spectra of these earliest quasars will analyze the chemical fingerprints of the gas around them, revealing their feeding habits and the conditions of their birth. While Webb dissects the ancient light, another colossal project will tune into the universe's magnetic symphony. The Square-Kilometer Array, a radio telescope network spanning continents, will map the sky with unprecedented sensitivity. Its primary mission regarding our cosmic monsters is to trace magnetic fields with exquisite detail. By observing the polarized radio emission from jets and lobes across millions of galaxies, the Square-Kilometer Array will finally chart the invisible architecture that shapes and directs relativistic jets. It will test the theoretical models of the Blandford-Znajek and Blandford-Payne processes directly, watching how magnetic energy is extracted and transformed. It may even detect the faint radio whispers from the accretion flows around quieter black holes, giving us a complete census of activity in the local universe. Yet all these telescopes share one limitation: they observe the light emitted by matter outside the event horizon. To probe the darkness itself, we must listen for the vibrations it creates in the fabric of space-time. This is the promise of the Laser Interferometer Space Antenna, or LISA. This future space-based gravitational wave observatory will detect ripples at much lower frequencies than ground-based detectors. While LIGO and Virgo hear the final chirp of stellar mass black holes merging, Lisa will listen for the deep, rhythmic hum of supermassive black holes dancing in the centers of merging galaxies. It could detect the slow in-spiral of smaller black holes or neutron stars as they finally plunge into a galactic giant, probing the space-time geometry just outside the event horizon in a way light never can. Each of these tools targets a fundamental mystery. Can we observe the chaotic plunge region inside the innermost stable orbit, where Einstein's gravity meets the unknown? What is the precise recipe of magnetic fields, spin, and accretion rate that determines whether a black hole shines as a quasar, a radio galaxy, or a blazar? And ultimately, what do the populations and behaviors of these objects, from the earliest times to the present, tell us about the underlying laws of gravity and quantum mechanics in the most extreme regime nature offers? The quest is far from over. It is accelerating, promising a future where the paradox of light born from darkness is not just a concept, but a detailed, dynamic story we can watch unfold in real time across the entire history of the cosmos. The brightest light emerges from the deepest dark. This cosmic truth transcends mere astrophysics, inviting us into a profound philosophical reflection on the very nature of existence. For if the universe's most brilliant beacons are powered by its ultimate voids, what does that tell us about the fabric of reality itself? It presents a powerful metaphor reminiscent of the mythical phoenix. From the ashes of consumed stars and annihilated gas, new light and structure are born. The supermassive black hole, a symbol of absolute destruction, becomes an unlikely agent of creation, forging light, sculpting galaxies, and seeding the potential for new worlds. This is not a gentle process. It is a cycle of cosmic violence and rebirth, challenging our comfortable notions of a serene, life-friendly universe. The late astronomer Carl Sagan often reflected on our humble place in the cosmos, noting that we are made of star stuff. But we must now add a deeper, more startling layer. The very elements that compose us and the stable galactic homes that allowed those stars to form may owe their existence to the regulating fury of these dark engines. This intertwining of creation and destruction touches on fundamental concepts like entropy, the universal trend toward disorder. A black hole represents maximum entropy, a sink of information and order. Yet around it, we see magnificent structures emerge, jets and lobes and heated gas that create new patterns and complexities. It is as if the universe uses these ultimate sinks to drive new forms of organization on a grand scale, a cosmic recycling program of breathtaking scale. Consider a more tangible, though rare, possibility. The relativistic jet from an active galactic nucleus, a beam of pure destruction, might travel millions of light years before striking a lonely, pristine cloud of hydrogen. The shock of that impact could compress the gas, triggering the collapse that leads to star formation. In this distant, unintended consequence, a force of annihilation becomes a midwife for new solar systems. This possibility directly challenges a human-centric view. We often imagine life requiring quiet, stable orbits around calm stars. Yet the history of our own galaxy suggests it too had an active, quasar-like phase in its youth. The very processes that seem hostile to life, the violent feedback and searing radiation, may have been necessary to create the conditions, the heavy elements, and the regulated galactic environment that eventually allowed our solar system to form. We are not here in spite of that ancient cosmic violence, but potentially because of it. Understanding this physics does more than satisfy curiosity. It reframes our perspective. It suggests that creation and destruction are not opposites, but partners in a dynamic, ongoing dance. The darkness is not merely an absence, it is an active participant in generating light and form. So when we look up at a tranquil night sky, we might now see it differently, not as a static backdrop, but as a snapshot in a vast, dynamic story where even the darkest forces have a creative role to play. Does this change the nature of existence itself? Perhaps it reveals that existence is fundamentally relational, a continuous exchange where even the most absolute ends can be woven into new beginnings. The black hole's spin is a hidden reservoir of power. This is not the simple rotation of a planet, but a profound distortion of the fabric of reality itself. Imagine the space around a spinning black hole not as empty but as a viscous fluid. The immense rotation drags this fabric of space-time along with it, a phenomenon known as frame dragging. It creates a cosmic whirlpool called the ergosphere, a region outside the event horizon where nothing can remain stationary. Everything, even light itself, is forced to move in the direction of the spin. Within this warped region lies a staggering amount of energy, the black hole's rotational energy, stored not in matter but in the twisted geometry of space-time. This energy is not locked away forever. It can be mined. The theoretical possibility was first demonstrated by Roger Penrose. He showed that if a particle enters the ergosphere and splits in two, one fragment could be hurled into the black hole while the other escapes with more energy than the original particle had. The extra energy comes directly from the black hole's spin, slowing it down ever so slightly. This Penrose process is a beautiful thought experiment, but in the messy reality of an accretion disk, a more robust mechanism takes over. This is the Blandford-Znajek process, the likely powerhouse for the most formidable relativistic jets. Here, magnetic fields are the essential tool. Intense magnetic field lines, generated by the churning plasma of the accretion disk, become embedded in the ergosphere. As the spinning black hole drags space-time, it twists these field lines into a colossal coiled spring. This twisting generates a powerful electric voltage, turning the region around the black hole into a cosmic battery. This battery drives currents that flow along the field lines, channeling the rotational energy upward and launching jets of plasma at nearly the speed of light. The spin, therefore, is more than just a property. It is a critical fuel source. A rapidly spinning black hole can convert a significant portion of the mass energy of infalling matter into jet power, operating with an efficiency that far surpasses a non-spinning black hole. It helps explain why some active galactic nuclei produce such breathtakingly powerful and persistent outflows. But how do we measure the spin of an invisible object? Astronomers use a clever indirect method, focusing on the innermost edge of the accretion disk. That edge is defined by the innermost stable circular orbit. For a non-spinning black hole, this orbit is relatively far out. But as spin increases, frame dragging provides a stabilizing effect, allowing matter to orbit much closer to the event horizon. The closer the inner edge of the hot, X-ray emitting disk gets to the black hole, the more severely its light is stretched and distorted by the intense gravity. By analyzing the distorted X-ray spectrum with space telescopes like XMM Newton or Chandra, scientists can estimate the radius of that inner edge and thus infer the black hole's spin. A famous example is the supermassive black hole at the heart of the galaxy MCG 63015. Observations reveal an X-ray spectrum stretched so dramatically that it suggests an inner disk skimming incredibly close to the event horizon, indicating a black hole spinning at a substantial fraction of the maximum possible rate. This high spin aligns with the idea of a well-fed, efficient engine. So we must ask, is the spin the ultimate battery for the universe's most brilliant beacons? It appears to be a master regulator, determining not just if a black hole can power jets, but how powerfully and efficiently it can do so. The darkest force in space, it turns out, can store its energy in the very curvature of the universe, and light is the currency in which that energy is paid. A backyard astronomer with a modest telescope can point it toward the constellation Canes Venatici and see, not just a fuzzy patch, but a brilliant, star-like point at the heart of the spiral galaxy NGC 4151. This is not a foreground star. It is the searing light of a supermassive black hole's accretion disk, a cosmic beacon close enough for us to dissect in fine detail. This is a Seyfert galaxy, our seventh and perhaps most vital object, a nearby, accessible laboratory where the violent physics of active nuclei is laid bare for study. Unlike the distant, overwhelming brilliance of quasars, Seyfert galaxies are often relatively near, spiral galaxies with normal structures, save for one extraordinary feature, an intensely bright, compact nucleus that can outshine the billions of stars in its surrounding disk. Their proximity and their distinct, star-like cores make them perfect subjects for the most powerful tool in the astrophysical arsenal, spectroscopy. When astronomers like Richard Green, who has spent decades surveying these objects, train a spectrograph on a Seyfert nucleus, the resulting rainbow of light is scribbled over with a forest of bright and dark lines. Each line is a fingerprint telling a story of temperature, composition, and most importantly, motion. The most dramatic features are the broad emission lines smeared over a wide range of wavelengths. This broadening is not a blur, it is a Doppler map. It reveals clouds of gas orbiting the central black hole at terrifying speeds, thousands of kilometers per second, within the gravitational grip of the monster itself. This is the broad line region, a maelstrom of gas just outside the accretion disk, but the spectrum also shows another set of lines, sharp and narrow. These come from gas much farther out, moving more sedately in the galaxy's spiral arms, illuminated by the central engine's radiation but not bound to it. This is the narrow line region. The presence or absence of these two sets of lines creates the fundamental Seyfert classification that supports the unified model. In a Type 1 Seyfert galaxy like NGC 4151, our view is relatively unobstructed. We see the brilliant accretion disk directly, and its spectrum shows both the broad lines from the fast inner gas and the narrow lines from the distant gas. Our line of sight peers directly into the fiery heart. In a Type 2 Seyfert, the view is blocked. A thick, donut-shaped torus of dust and gas orbiting the black hole obscures our direct view of the accretion disk and the innermost broad line region. We only see the narrow lines from gas above and below the torus, illuminated by the central engine's radiation that escapes through the poles. The archetypal Type 2 Seyfert is the beautiful galaxy NGC 1068, also known as Messier 77. Through an optical telescope, it looks like a normal, face-on spiral with a bright, compact core. But spectroscopic observations across the electromagnetic spectrum reveal the truth. X-rays and infrared light, which can penetrate dust, show the hidden powerhouse, while optical light shows only the narrow lines. This single observational difference, dictated solely by our viewing angle, was a cornerstone in developing the unified model of active galactic nuclei. Modern studies use a technique called integral field spectroscopy. Instead of taking a single spectrum of the nucleus, this method takes thousands of spectra across the entire galaxy, creating a three-dimensional data cube, 2 dimensions of space and 1 of wavelength. Teams using instruments like the multi-unit spectroscopic explorer on the Very Large Telescope can now map the velocity and ionization of gas not just at the core, but across the entire galactic environment. They can watch how the fierce radiation from the nucleus excites and pushes gas, tracing the feedback process in action. They can even map the structure of the obscuring torus itself by studying how it absorbs and re-emits light. This leads to a pivotal question. What can these accessible laboratories tell us about the torus, that crucial structure that both feeds the black hole and hides it? Observations suggest it is not a static, solid ring. It is a dynamic, clumpy cloud of molecular gas and dust, likely the reservoir from which the accretion disk is fed. Some material spirals inward to fuel the engine, while radiation and winds from the engine blow other material away, creating a constant, turbulent cycle. Studying Seyfert galaxies allows us to witness this feeding mechanism in exquisite detail in our cosmic backyard. They remind us that the brilliant quasars of the early universe were not alien abstractions. They were extreme versions of phenomena still quietly at work in galaxies we can see on a clear night, proving that the partnership between light and dark is not a relic of the past, but an ongoing, intimate dance. 670 million years after the Big Bang, a monster was already awake. The quasar known as J0313-1806 shines from that impossibly early epoch, powered by a black hole with the mass of 1.6 billion suns. Its existence poses a profound timing problem for cosmologists. How did such a titanic dark force assemble itself in what amounts to a cosmic blink of an eye? This is the puzzle of the first black holes, the mysterious seeds of darkness that must have taken root before the universe was even 1 billion years old. The conventional growth story is too slow. Imagine starting with a black hole formed from the collapse of a single massive star, a stellar remnant of maybe 100 solar masses. Even if it fed continuously at the maximum theoretical rate, the Eddington limit, it would need far more time than the early universe provided to reach billion solar mass proportions. There simply wasn't enough time on the cosmic clock for these behemoths to grow from such modest beginnings, so theorists must look for more massive seeds, born not from stars but from the raw conditions of the infant cosmos. One leading candidate is the direct collapse black hole. Picture a pristine cloud of hydrogen and helium falling into one of the universe's first dark matter halos. In this unique environment, before heavy elements existed, the gas could not fragment efficiently to form many small stars. Instead, theorists like Priyamvada Natarajan, who models these early epochs, suggest the entire cloud, weighing hundreds of thousands of solar masses, could have catastrophically collapsed directly into a black hole. This would create a ready-made giant seed, a head start for the eventual supermassive monster. A second possibility involves the very first generation of stars, known as Population 3 stars. These pioneers were not like the stars of today. Born from pure hydrogen and helium, they are thought to have been colossal, perhaps hundreds of times the mass of our Sun. Such giants live fast and die young, collapsing into black holes of significant mass. While still smaller than direct collapse seeds, these stellar remnants could then merge rapidly in the dense early universe, building up mass through a frantic series of collisions. The role of dark matter is foundational here. Its invisible halos acted as gravitational traps, pulling in the primordial gas. The size and merger history of these halos dictated whether a cloud collapsed into a single massive seed or fragmented into a cluster of smaller stars. It was the unseen dark architecture setting the table for the first feast. The James Webb Space Telescope is now our most powerful time machine to probe this mystery. It is not just looking for brilliant quasars, but for their fainter, more numerous precursors, the growing black holes that have not yet ignited into full brilliance. By finding these adolescent monsters and measuring their masses and host environments, Webb can constrain which seeding mechanism dominated. Did the first darkness in the form of massive seeds precede the first stable starlight? Or did light and dark emerge together in a chaotic, co-evolutionary dance? The answer will rewrite the first chapter of cosmic history, revealing whether the universe's most powerful forces were born from the slow grind of stellar life cycles or the sudden, violent collapse of creation's first structures. The human mind has always woven stories from the stars, finding monsters and meaning in the dark. Long before we understood quasars or supermassive black holes, our myths were populated with cosmic devourers, beasts that swallowed light and heroes alike. These ancient narratives of all-consuming voids and radiant celestial gates reveal a deep, intuitive fascination with the very paradox science now confirms, that creation and destruction are eternally linked. The cultural journey of these ideas mirrors our scientific one, beginning with a speculative notion in the late 18th century. The English natural philosopher John Michell, applying Newton's laws of gravity and light, pondered the existence of what he called dark stars, bodies so massive their gravity would prevent light from escaping. It was a brilliant theoretical leap, yet it remained a curious footnote for over a century, a shadow in the equations waiting for the full theory of relativity to give it form. The term black hole itself, coined much later by physicist John Archibald Wheeler, carries a visceral, almost mythic weight, perfectly capturing the absolute and mysterious nature of the object. This evolution from dark star to black hole shows how scientific concepts, as they solidify, become new vocabulary for our oldest fears and wonders. They feed directly back into our stories. Consider the word quasar, a crisp, modern contraction of quasi-stellar radio source. It sounds like something from science fiction, a pulsing beacon from a lost civilization, and that very sense of mystery has made it a staple in novels, films, and games, symbolizing ultimate power or a gateway to the unknown. The visual representation of these objects has become its own cultural artifact. The glowing, twisted ring of an accretion disk, bent by gravitational lensing, is now an iconic image. Its most famous depiction is the black hole gargantua in Christopher Nolan's film Interstellar. The filmmakers did not guess at its appearance. They enlisted physicist Kip Thorne to solve the equations of general relativity, rendering the disk's light with scientific accuracy. The result was not just a stunning visual effect, it was a piece of public science communication, introducing millions to the real, warped geometry of spacetime around a spinning singularity. This collaboration highlights a vital trend, the growing dialogue between scientists and storytellers to depict cosmic wonders with fidelity. Accurate portrayals matter because they shape public understanding. When a film like Interstellar takes care to show time dilation near a massive object, it teaches a complex relativistic concept through visceral experience. Conversely, sensationalized depictions that treat black holes as simple cosmic vacuum cleaners can perpetuate misconceptions, missing the nuanced truth of their role as dynamic engines. Science communicators play a crucial role here, translating the mathematics into narratives that capture both the awe and the accurate mechanics. This cultural resonance points to something fundamental about us. Why does the juxtaposition of a brilliant disk against an absolute dark sphere feel so profoundly compelling? It resonates because it mirrors core human themes, the struggle between light and dark, knowledge and oblivion, the finite and the infinite. The black hole is the ultimate unknown, the modern abyss, while the quasar is the defiant, brilliant structure we build at its edge. Our art and our science are both ways of building that structure, of imposing light and meaning on the terrifying and wonderful dark. This cultural feedback loop enriches our exploration, reminding us that to understand the cosmos is not just to collect data, but to continually reinterpret our place within a story that is both physically real and deeply, enduringly human. Even with all we have uncovered, the case file on these cosmic engines remains thick with unsolved puzzles. Each unanswered question is not a failure of science, but a doorway to new physics, a signpost pointing toward a deeper layer of reality we have yet to map. Let us review the outstanding mysteries, the gaps in our understanding that keep astronomers and theorists awake at night. First, the precise mechanism of jet launching and collimation. We know magnetic fields and spin are involved through processes like Blandford-Znajek, but the exact choreography is murky. How are particles accelerated to such phenomenal energies within the jet? What determines whether a jet is a steady stream or a series of violent blobs? Observations from the Event Horizon Telescope and future polarimetry studies, which map magnetic field structures, are our best hope for decoding this cosmic propulsion system. Next, the physics of the accretion flow in the plunging region inside the innermost stable circular orbit. This is the final descent, where matter stops circling in a stable disk and makes its fatal plunge toward the event horizon. General relativity predicts this region, but the behavior of magnetized plasma here, where gravity is strongest and time is severely warped, is a frontier. Does the material radiate its last energy here, or does it vanish silently? Capturing this requires observing the most rapid X-ray fluctuations from objects like our own galaxy's quiet black hole, Sagittarius A star, during its rare, faint flares. Then there is the nature of the corona that produces the hard X-rays. Above the accretion disk of many active black holes, a cloud of superheated electrons seems to exist, a corona akin to the Sun's but far more energetic. This corona is likely the source of the high-energy X-rays we detect, but its origin is debated. Is it the base of the jet, a region of magnetic reconnection, or a wind rising from the disk? Understanding this requires precise timing, watching how changes in the disk's optical light echo in the corona's X-ray output milliseconds later. The origin of the broad line region clouds presents another enigma. These are the dense clouds of gas whirling around the black hole at thousands of kilometers per second, whose smeared light gives us the broad emission lines in quasar spectra. But what creates and sustains them? Are they condensations from a disk wind, or the shredded remains of stars passing too close? Their dynamics are a direct probe of the black hole's gravitational influence, yet their very existence is a puzzle of stability in a violently hostile environment. Even the familiar Aegean dust torus, that crucial structure that feeds the black hole and hides it from certain views, is not fully understood. Is it a smooth, donut-shaped ring or a dynamic, clumpy swarm of molecular clouds? How does it withstand the intense radiation blasting from the core? Its exact geometry and composition remain actively debated, with observations across infrared wavelengths trying to piece together its true form. All these mysteries, however, point toward the ultimate foundational puzzle, the true nature of black hole singularities. This is no longer a problem for general relativity alone, but for a theory of quantum gravity that does not yet exist. What happens at the point of infinite density where our current laws of physics break down? Is there a firewall, a fuzzball, or a bridge to another part of the cosmos? This question lies at the intersection of the very large and the very small, and answering it may require a fundamental rewrite of our understanding of space and time itself. So we are left to ponder, looking at this list of cosmic cold cases. Which mystery do you think will be solved first? Will it be the detailed blueprint of a jet, revealed by a next-generation telescope array? Or will a sudden insight into the quantum nature of gravity crack the singularity's code from an unexpected direction? Each answer will not just fill a blank in our textbook, it will reshape our story of how darkness and light conspire to build the universe. The night sky from a quiet backyard is a portrait of perfect stillness, a scattering of diamond points on a velvet sheet. It is a profound illusion. That serene vista masks a reality of unimaginable violence, of monsters feasting and galaxies colliding in the deep. Our journey through these extremes of light and dark is more than a catalogue of cosmic phenomena. It is a mirror held up to our own deepest curiosity. It reveals a humbling truth: the same laws of physics that govern the fall of an apple or the glow of a light bulb also orchestrate the brilliant scream of a quasar and the silent spin of a black hole. The universe speaks one language, and we are slowly, painstakingly learning to listen. This perspective shift is something astronauts describe with awe: the overview effect. From orbit, they see Earth as a fragile, blue marble suspended in a vast, black emptiness. That view dissolves borders and highlights our shared home. Our intellectual journey offers a similar overview, but across time and scale. We see our planet not just as a place, but as a participant in a grand cosmic cycle. The iron in our blood was forged in the heart of a dying star. The very atoms that make us may have been scattered across the galaxy by the fierce winds from an active galactic nucleus, that same violent feedback that regulates star formation. We are not just observers of this story, we are literally made from its chapters. Our quest to understand this violent cosmos has yielded unexpected gifts here at home. The drive to peer deeper into space has spun off technologies that shape our daily lives. The image sensors in our phones trace their lineage to astronomical cameras. The algorithms that filter data from the Vera C. Rubin Observatory share DNA with medical imaging software that helps diagnose illness. The pursuit of pure knowledge, of answering a fundamental question about the nature of light and dark, tangibly improves the human condition. It is a powerful reminder that exploration, whether outward into space or inward into equations, is a defining human trait. Consider the chain of events required for you to learn about a quasar. A supermassive black hole, 1 billion times the Sun's mass, tears matter apart in a blaze of radiation. A fraction of that light travels unimpeded for billions of years across the expanding gulf between galaxies. It finally enters a telescope, a machine built by a species that learned to shape glass and silicon and metal. The signal is converted, analyzed, and understood by a mind that evolved on a planet orbiting an ordinary star. That beam of ancient light, born from the darkest force, culminates its epic journey as insight in a human brain. What does this say about us? It suggests that curiosity is our own brightest beacon. In a universe that can be indifferent and violent, we have chosen to seek meaning, to map the chaos, and to find our place within it. We use the quiet, consistent laws we discover on Earth to decode the most spectacular fireworks in creation, bridging the gap between our local reality and the cosmic extremes. This ability to comprehend monsters we will never visit, to feel wonder at processes that dwarf our existence, is perhaps our most profound connection to the cosmos. It prepares us for a final, synthesizing thought, one that ties the violent paradox we began with back to the very nature of reality itself. A brilliant quasar and a silent black hole are not opposites, but two faces of the same cosmic engine. This journey has taken us from the blinding lighthouses of the early universe to the hidden, spinning singularities that power them, revealing a universe where creation and destruction are partners in an eternal dance. We have met the diverse cast of characters, the brilliant quasars, the beamed blazars, the varied active galactic nuclei, and the fleeting stellar snacks of tidal disruption events. Yet beneath their different appearances lies a universal physics, the elegant and violent choreography of accretion, magnetic launch, and relativistic jets. This relationship is far more than a spectacular paradox. It is the fundamental engine of galactic evolution. The fierce feedback from these bright dark hearts regulates star formation, heats galactic halos, and ultimately determines the size and shape of the galaxies we see today. It is a testament to a deeply interconnected cosmos, where the most extreme forces are woven into the fabric of cosmic growth. The ongoing dance between gravity's relentless pull and light's radiant push sculpts the universe on its grandest scales. As our tools grow more powerful, from the Vera C. Rubin Observatory's relentless sky scan to the future Gravitational Wave Observatory, LISA deep listening, each new discovery will further illuminate this beautiful and violent partnership. Thank you for exploring these cosmic extremes with me. If this journey into the heart of darkness and light sparked your curiosity, please subscribe for more deep dives into the mysteries of space. And let me know in the comments which of these brilliant objects born from the darkest forces fascinates you the most.